Thank you all for coming. My name is Gjeta, and this is James. James and I are part of a team at Morgan Stanley that has built a platform on which other developers across the bank can write applications to support the business directly. Our team also controls the runtime so that we ensure that these apps that the developers write can run in the way that developers want them to run. So our clients are first and foremost other developers. And our overarching aim is to build our platform in such a way that our developers can write the code that they want to write and to control the execution of that code so that it runs the way they want it to run. So our developers get to focus on business logic without concern for parallelization or batching or caching or distribution or any other infrastructure. The execution concerns don't pollute the type system, and that's our main aim. I am a developer on the core technology that we're presenting to you today. So that covers the compiler plugin, the scheduler, and the cache, and a load of other cool things. And I joined the team about a year and a half ago. James has been involved with the project since it began about 7 years ago, and I don't really know what he does all day. But he has seen the project grow into one of the biggest Scala code bases in the world, with over 3 million lines of code and more than 20,000 pull requests into our main branch by over 500 active developers worldwide. Of those 3 million lines of code, about 60,000 cover the core technology of the platform itself, and the rest is application code built by developers on top of the platform. And this ranges from trader desktop applications to risk calculations that run at the end of every day or throughout the day. And of the 500 developers, only about 50 work on the core technology itself. Some of you here may have seen our first talk back in London in Scala Exchange about 6 months ago. And there we introduced our platform as a technology that could automatically parallelize user code. But that wasn't the whole story, and that's kind of why we're back again today doing another talk. The problem is that we can't talk about parallelization or multi-threading without talking about thread safety. And we can't talk about thread safety without talking about change. As someone wise once said, I forget the name, some Greek guy, change is the only constant. And that means that as developers, we have to deal with change. Do you hear music?
Yeah.
That wasn't planned. Does someone have their phone on? Cool, okay. So as developers, we have to deal with change. And change is inevitable. In any real system, any long-running application that's live for more than like 2 seconds, we have state, and that state is immutable. And the things that cause this change might be as simple as time ticking forwards, or prices and temperatures fluctuating, or users updating their preferences. Wow, there's the music again. Okay.
I think it's in the next room.
You think so? Oh, it's the other room. Oh, you guys should all go there. It sounds way more fun. So, yeah, change can be caused by a lot of different things, and we have to deal with it. But our challenge is to use the benefits of immutable state in a multi-threaded environment, but without forcing developers the ability to easily deal with change, and without incurring some of the costs that different programming paradigms enforce on us when we try to deal with change. And James is going to talk about that next.
Just before I do, there's lots of people standing up. Can you squidge to the middle? If there's a seat to the middle of you, can you just move in so that people can sit down? There's like a bunch of seats down the front.
Yeah, good idea.
Thanks very much. Okay, so I'm going to talk a little bit about how we manage change, and I'm going to focus on the kind of two big programming paradigms, procedural OO and subsequently functional. So I'll first talk about dealing with change in procedural programs. Like when we mutate things in procedural programs, like in single-threaded procedural code, things are actually quite nice, right? The stack frame marches forward. You can put breakpoints in the code. Like typically, it's highly repeatable if there aren't threading concerns, and that's really good when you're trying to like find problems, figure out how the state got into the state that it's in. But with procedural programming, when you introduce many threads, and I don't know how many people have debugged multi-threaded code, you kind of wind up in this thing where your mind is trying to track all these things that are happening simultaneously. And it's really hard to find out sometimes like this, how you got into a state that you got into. And it's really difficult then also because you can't put breakpoints always in an individual thread, because if you stop that thread from progressing, it won't replicate the problem that you're trying to debug. So you get into these kind of nasty situations with procedural programming and change, where it can become like a bug hunt from hell, and it takes a very long time to get to the bottom of a problem. So procedural programming definitely hasn't nailed it. I do want to, before I move on to talk about functional programming, just talk about the syntax. Like with procedural programming, it's actually like very clean and simple. Like at the kind of change site, at the point where you make a change, it's really easy to understand what's happening. All the locking and all the message passing and all the other things that go along with that are not easy to understand. But the actual point where you make the change, that's a very easy thing to understand. So let's talk a bit about functional programming. We want to kind of go through like two significant problems that you run into when you use functional programming paradigm with and you try and have change in your system. So the first problem is it creates code that's hard to read and difficult to write. And so to illustrate this, we're going to bring back some code that we used in our first talk. So people who saw our first talk, we like parallelized the execution of this code. In this talk, we're going to talk about how we would deal with change on this code. So this is a pretty simple example. There are 3 classes, and we'll create one of each, so there'll be 3 objects. The flight object contains a fuel cost object, and the fuel cost object contains an FX rate object. It's a pretty simple ABC relationship. But even this, when you start to want to introduce change, it's not straightforward in a functional paradigm. So in a functional paradigm, you don't actually change anything. You always create new. So in that model, if I want to, for example, change this rate variable inside of the FX rate, like once I've created this thing, I want to go in there and change it, I have to write this kind of code. So I have to create a new A, a new B, and a new C. In this case, it's a new flight, a new fuel cost, and a new FX rate, and glom those together. And now I've got my new state, which has got this one change in it. Now, there are helpers for this. There are things like lenses, and I've got an example here which shows how lens syntax is much nicer. But you still have this. This isn't really like expressing the change that you're trying to make, because you're manipulating the flight object, which has really nothing to do with your like intended change, which is to change this FX rate, right? So there's a kind of, it's not a great from a programming usability perspective. And the other thing is that even though you can put these nice wrappers and helpers around these things, it doesn't change the underlying mechanics, and I'll talk a bit about why that's problematic as well. So I've also put up what would be the simplest case, which is what I'd like to write, but we don't have ways to write this kind of simple thing. So let's talk about the actual complexity that you encounter in a real system. So I showed with 3 objects, but really like real systems have like numerous objects. So I've sort of made this code slightly more complicated. And so now the flight contains an occupancy score, and this occupancy score is something that airlines use quite a lot. So they'll work out, is it more likely that people are going to book onto this airplane, depending on when people have holidays and things like this. But some occupancy scores are affected by exchange rates. So for example, like when the pound-dollar exchange rate goes favorable to people from the UK, like lots of people from London get on a plane and come go shopping in New York. Right. So it's reasonable to assume that various things are affected by the FX rate, not just one thing. So let's look at the object graph for that. We do not have an art budget, so I got my children to draw the object graph. But it's an accurate rendition. The big object on the left there, that's the flight, and then the flight contains the fuel cost and the occupancy score, and the fuel cost and the occupancy score both reference the FX rate, but only one of them references the local price. So you wind up with this kind of, it's a pretty simple object graph, right? So let's talk about now what happens in this still relatively simple object graph if I want to change the FX rate, right? I have to do something like this. So I've got to work out which of the new objects to create, and then I have to actually create an interim variable, because otherwise it's kind of hard to write, and then I have to do this. Now, what you can do is, if you want to follow the functional paradigm, is you can kind of contort your object model so that you mostly deal with like a directed graph, so that then you can always use a lens type construct. But then it's kind of, the code that you've got above there, that's kind of nice to read because it's a good representation of the business problem that you're trying to solve. So that's not great either. So in terms of expressibility, it can be hard to create code that's easy to read and expresses the problem that you're trying to solve. And I also got them to draw this picture just to like represent what really happens in a real system. And so you can imagine like, well, I want to change the value of one of these like orbs. It's a big deal. Like there's a lot of code that's involved in that, and it's hard to understand. So that's the first problem with functional model. The second problem is really around efficiency. Like copying things is not free. Like when you copy something, you will always pay the price later when the garbage collector comes along to like hoover it up. So when you build like very high performance Java systems, you spend a lot of time trying to reduce the amount of allocations that you're doing because it makes things faster. Rory isn't here, but Rory built this profile for us, and this is like just a profile extraction from the Scala compiler. And those guys at Lightbend, they really know what they're doing, and they spend a lot of time optimizing the compiler, but still the use of functional constructs has still driven that thing to generate quite a lot of objects. So this is like an output from compiling Akka. It's about 33,000 lines of Scala. And during that compile, the compiler like allocates 75 million objects. So that's all stuff that then the garbage collector has to come along afterwards and clear up. So for these reasons, like our kind of what our sort of starting point is that when you manage change in like an app, we haven't, as an industry, we haven't really nailed a good way to do it.
All right, if there's one thing I've learned from coming to these conferences is that it's that no Scala presentation is complete without a little bit of theory. So I'm going to spend a few minutes talking to you about an idea that is really crucial to our solution. And it's become this all-powerful building block on top of which we build kind of everything. And that's represented here by this software superhero, Referential Transparency Man. Again, thank you to James's children. So a lot of you may be familiar with this idea already, but I'm going to take a few minutes to explain anyway, just because it's so important. So a function is referentially transparent if it returns the same result every time I call it. So given the same input, I'm guaranteed to get the same output no matter where or when I call it. Or to put it yet another way, a function is referentially transparent if I can substitute calls to that function in my program directly with the result without any observable impact on the behavior of the program. So let's take a look at a couple of examples. In this case, my function x takes some input parameter I and just computes 3 plus the log of I. And in foo, I'm calling x with an input parameter of 10. And as I mentioned, substitutability is key. So in this case, we can just replace that call with its result, and we have no impact on the behavior of foo. So this is good. X is referentially transparent. So let's take a look at a counterexample. This time, x is a call to get the current time, and foo is a function that takes some input parameter, another time, and just checks whether your input is after x. So the time now is 2:30. So let's say I run this function foo with an input parameter of y equals 3 o'clock. 3 is after 2, and so this function returns true. But let's say that now I try that trick again, where I substitute the method body this time wherever I see x in my program. So now I'm making calls to get the current time directly. And let's say that I run this function again now at 2:30 with the same input parameter, y equals 3 o'clock. And foo is going to return true. And I can keep running foo, and it's going to keep returning true for a little while. But as soon as the clock hits 3, it's going to start returning false. So even though I'm calling foo with that same input parameter of y equals 3 o'clock, suddenly it's returning a different result. And that's because I'm relying on behavior that's inherently not referentially transparent. But why do we care at all? Well, like any good superhero, Referential Transparency Man has some superpowers. And what referential transparency gives us is a number of immediate benefits. The first of these is order independence. Because these functions are guaranteed to return the same result every time I call them, I can run them in any order. It doesn't really matter. So we're free to reorder execution. And that leads to parallelism. We can run these functions in parallel because they won't interfere with each other. They're independent. And we can run them asynchronously. It doesn't matter whether I block to wait for the result or whether I get a callback and get that result later. It's still the same result. The other thing we get is portability. So just like I can run this function across multiple CPUs, I can also run the function across an entire grid of machines, and I'm still guaranteed to get the same result every time I call it. But the benefit that we're going to focus on today is caching or memorization. So because these functions are guaranteed to give the same result, I can look up the call to the function in a cache and just retrieve the result if I've already got it, rather than recalculating. And you can imagine the benefits if my function is CPU intensive or is making lots of I/O calls. I can save a lot of time by just going straight to the cache and getting back the result. And I know that people are kind of scared of caching, and cache coherence is one of the hardest problems in computer science and everything. But we don't worry about that because of the guarantees of referential transparency. My functions are guaranteed to return the same results every time I call them. And so I can just retrieve those results from the cache. So far, this idea of referential transparency maybe conflicts a bit with the idea of change, but it allows me to introduce our solution, so I can talk about it later. So we've created this construct, the node, and this is an annotation that extends the Scala language, and we've implemented it ourselves using a compiler plugin. So when you, the developers, annotate your function as a node, you're guaranteeing to the compiler that that function is referentially transparent. And that's up to the developer to ensure, and we were kind of paranoid about this when the project first started out, and so we built tools to check whether functions actually are referentially transparent. But in practice, we haven't had to use those, because it turns out that most people are able to do this easily, and most referentially transparent functions just make calls to lots of other referentially transparent functions and then glue together the results. When we see a node in the code, or a function annotated as a node, we don't compile it using the conventional Scala compiler. We use something called Scala async, and that generates like a state machine representation of the function. And in our last talk, we talked about how that lets us automatically parallelize and asynchronize this code. So at compile time, we're forming these representations of referentially transparent functions, and these representations let us, at runtime, take advantage of some of these benefits of referential transparency. But at runtime, we need something smart to actually control execution of these things, and that's where our scheduler comes in. So the nodes, or the functions on the right of the screen, form work items, and they put them into the scheduler's work queue. And the scheduler can look ahead in that queue, and it can make intelligent decisions about how to execute the code. So if it sees lots of calls to a database, it can batch those calls. And we talked a bit about that in our last presentation. But it can decide to run these nodes in parallel or even across a grid of machines. And this goes back to our aim. We don't want the developer themselves to worry about execution plan. They focus on business logic, and it's kind of a trade-off. They hand over responsibility for execution to the platform itself. But the key thing to note here is that the scheduler is cache-aware, and that's what we're going to focus on in today's presentation. So before we actually run any code, we look up a result for that function in the cache. And if it's already in the cache because we've run it before, and we know it's referentially transparent, we can retrieve it directly from the cache rather than executing the body of the method again. But you guys don't have to believe me, because we're going to show you how this works in a demo. And for this next part, I am going to keep talking while James types, because we can't multitask. And we're going to start off with a very basic example, then build up from there. So suppose I have some function calc, and it just multiplies two numbers together and prints a calculating line. And I've annotated this as a node because it's referentially transparent. That result there is never going to change. So we call calc, and you see what you expect to see. We print that calculating, and then we multiply the two numbers and return the result. But now let's see what happens when we try and calc again. This time, the only difference is we don't see calculating, and that's because we're not actually executing any code. We've looked it up in the cache, and we get a cache hit, and we retrieve the result directly from the cache. And we can do that again, and again, the scheduler looks up in the cache before it runs the code, and we get the result. So I've been talking about caching, but to actually be able to address something in a cache, you need addressability, and that's what referential transparency gives us. It kind of gives us this concept of being able to address a function and give it some identity and give us a cache key. And in this very simple case, the function name itself is enough as a cache key, because every time we call the same function calc, we look it up by that function name and we retrieve it directly from the cache. So let's make this a little bit more exciting. This time, this function calc, once James figures out that, oh my God, I think you compiled something.
Oops.
Okay, so this time,
No, it
yeah, it doesn't really matter. Just stop it. Yeah. Okay, so this time, it's the big square. Yeah, that one.
I know, but I can't see the screen because of the light.
This time, my function calc takes some input parameter quantity, and it prints that print line again, and then it multiplies a number by quantity. So we can call calc with an input of 20, and we run the calculation, and we return a result. But now let's say we try and call calc again with that same input parameter. If you're following me so far, you will guess that now we don't print that calculating, and that's because we're not running the method body. We're just retrieving this result directly from the cache. But let's see what happens if we try and call calc with some different input parameter, 40. Well, 40 is not in our cache yet, because we haven't run this one before with this input parameter. And so we print line calculating, and then we return the result. But now if we try again to call calc with that input parameter of 40, we retrieve it from the cache directly. So the key thing here is that calc is still referentially transparent. Even though its output is changing, it's only changing as a function of that input. So given the same input, I am guaranteed still to get the same output. But the parameters now need to form part of the address space. Yep.
You rerun again calc 40 again.
Yeah. Oh, it's from the cache. So just to repeat it for anyone who didn't hear, if we run this again with an input parameter of 40, is it going to hit the cache?
The previous value, right?
This one?
20.
So there's 20. That's a cache hit. Yeah, and 40 as well as a cache hit. And any new parameter is going to be a cache miss because we haven't done it yet. Yeah, 14 is cache miss, so we see the print line again. Right, so our function name on its own is no longer enough to form the cache key, and we now need to include that parameter. But with that, if we call the same function with the same input parameter, it's still referentially transparent, and so that is now enough to form the cache key. We can get a cache hit and retrieve directly from the cache rather than run the calculation. Okay, so now let's suppose that this function calc is actually a method on some instance. So we have this fuel cost class, and that contains an FX rate and a price. And our function calc from before now depends on one of the, well, actually both constructor parameters, price and the rate, and on our input parameter, quantity. So let's say we construct some fuel cost. We've already got an FX to save us typing. That's it there, and typo. We can construct fuel cost using that FX rate and some price 20, for example. 30, okay. Okay, so we have our fuel cost, and we can now call this method calc on the instance f of fuel cost, and we can call it with the same input parameter 20 as before. But this time, our function calc depends on the constructor parameters, and so we haven't actually calculated this before, so we see that print line calculating, and we get the result. But if we try this again with the same input parameters, we retrieve directly from the cache. And that's because we're now taking into account instance identity. And we can construct, well, yeah, okay, we can run this calc again with some different input parameter 40. And again, we'll have to actually run the execution because it's not yet in the cache. But the key thing is that calc is still referentially transparent given the same instance identity and the same parameters. So if we construct a different fuel cost G, where the price is now 42, then because calc depends on that, that constructor parameter, if we try to call calc with the same input parameters again we get a cache miss. So we have to actually run the calculation and return the result. But again, if we call it with the same input, then we're going to get the same output directly from the cache. So this time, again, we get a cache hit. So it's no longer enough for us just to take into account the function name and the parameters. Now we need some concept of instance. And we've created this construct called an entity. You see the annotation on the class there. That gives us instance identity. Case class equality and identity works similarly to Scala case classes for entities. So now, given the same instance and the same function with the same input, our function calc, our node, is guaranteed to give the same output. And that means that we can cache that result rather than looking it up. And we can address calls to this function in order to be able to get that cache key. Okay, let's make it a little bit more complicated. Well, actually, no, let's get to the point and do the thing where we deal with change. So far we've kind of shown you the build-up. But now let's suppose that we want to be able to change the FX rate like James did in his example beforehand. So we have constructed this thing called a scenario. And a scenario holds a bunch of intents to make a change. And those intents are called tweaks. So a tweak represents your intent to make a change to a node. And the scenario then holds a collection of those things. You've got a typo, it should be val.
Oh, sorry.
So we're trying to keep in line with the functional paradigm where our code is as expressive as possible. We want to express what we're trying to do rather than how we're going to do it. So we can write a scenario, and a scenario...
I need to make a fuel cost first.
Don't you have one?
Oh, that's true. I've got one.
We've got a fuel cost. It's called F. Yep. Okay, so we can construct a scenario, and a scenario will hold a bunch of tweaks, one of which will be our f dot fx. Is it called fx rate? No, dot local currency. Yep, dot rate. Right, so this tweak expresses our intent to change the rate to 8.13. You've got a typo. Yep, this is good teamwork. Okay, and then close bracket, yep. So we have a scenario, and the scenario is holding on to all of our intents to make a change. So that's kind of, we're constructing this one extra object, the scenario. But we haven't actually applied the change anywhere else. Sorry, to do this, I forgot to mention that some of you will have noticed, rate is marked as a node. And that's what allows us to do this tweaking. So if we just run f.calc with that same input parameter of 20 again, nothing will have changed. And in fact, we can look at the rate that's on this fuel cost object, f.local currency, yep. The rate is the original rate that we constructed it with, 8.88. And our scenario contains our intent to change this rate to 8.13. But now we need to actually apply the change. And so we have a construct called a given block. And a given takes a scenario and then runs any computation in that scenario with the change applied. So if we run this again with the same input parameters, this time under this new scenario, we see that we have to run the body of that method again. So we see the print line to calculating and a new result. But if we're in that same scenario again, and we run f.calc again, are you just going to copy paste?
Exactly.
Yeah. Then this time we're going to get a cache hit. And that's because my function calc is still referentially transparent under certain conditions. So in the same scenario, on the same instance, the same function with the same parameters is referentially transparent. So when we run it again, we get just the result directly from the cache. We can, what do you want to do? Well, we can actually show that if we come back out of this scenario, so if we just run f.calc with the same input of 20, we haven't irreversibly changed the rate. There's no mutation that we've done here. But the platform itself has managed the propagation of change throughout our dependency graph. So this time we don't need to understand the whole dependency graph. We don't need to kind of bend it into shape to make it easier to do this with lenses and so on. The platform itself manages the change for us. And all we do is express our intent to change and then apply the change in a given block. But So this is pretty close to what developers want to write, but it's still not quite there. And so we've added some syntactic sugar in our given blocks that allows us to tweak nodes directly. So we can address this node again. Yep, you're good. And directly tweak it to 8.13. And then we can run that same calculation again. So the underlying mechanics are still the same. We still have a scenario. But we're much closer to that nice, mutable, procedural way of changing stuff. And we think it's much easier to read this kind of code than to read functional style change. So our cache key is no longer sufficient as it is. We need to take into account now the scenario. And that's because our function changes depending on the scenario that we're in, depending on the value of this node. So as well as instance identity and all the other things, we now take into account the scenario. And this kind of completes our cache key. This means that we can look up a function with certain input parameter on a certain instance within a certain scenario and still get cache hits against that. And that's a pretty huge saving. I mean, this is a dummy example, but it's a huge saving when you're running big CPU-intensive calculations that can potentially reuse a lot of data from cache. Okay, so let's take a look at the more complicated example that James showed you before, where we had the hands holding onto the objects. So this time we have this flight, and I think we've already constructed one. Whoa. And a flight contains a fuel cost that we had before, but it also contains occupancy score, and occupancy score also has an FX rate. We've defined two methods on flight. One of them is fuel cost, and that just calls calc, like we were calling before, on our fuel cost object, with an input parameter of, if I hover over this, we should be able to see. Oh, fuel quantity, which is in our constructor parameter. Okay. Yeah, 30. And we also have some other function, an occupancy score. But we can still change the rate in our fuel cost without understanding the entire dependency graph. So we can kind of do it in the procedural style, where we reference the flight.fuelcost.localcurrency.rate directly inside a given block, and we can set that to some new value, and then run our calculation again. Yep. And within that scenario, the change is applied, and we only invalidate the parts of the graph that need to be invalidated, which means that we don't lose out on any cache reuse. But the key benefit is that we don't have to understand the dependency graph. So our developers write the code that's as close to the code that they want to write as we can, but we keep all of the benefits of immutable state and referential transparency in a multi-threaded environment. Yeah, I think so.
Okay. Oh, didn't press the last down button. So to summarize, what we have is we have a way of allowing people to write change in a way that's really easy to read, but also we can execute that efficiently. Our the number of objects we're creating is like linearly proportional to the change that we're making, and then as Gjeta said, as we then run the calculation, we can see which things we need to rerun because we know where the change is, and that's all handled inside of the scheduler. This means that we think developers are more productive because they can write code that's easy to read and easier to write in the first place. And this all really comes back to the fact that we can logically address a function. So you can view it as like a mathematical universe where we can address the function inside of there. And because we can address it, we can cache it. But also because we can address it, we can simulate change on it. And that's really the kind of underlying premise of the whole thing. And that matched with like an understanding of referential transparency is extremely powerful. Around about now, a lot of people are thinking, well, how much overhead is there? So I asked Sergey, who is here, we have a profiler that we built, and Sergey and Dimitri are working on it at the moment. And he ran some apps for about a minute, like heavily multi-threaded apps. And in one case, there are about 4 million node functions, and it took about 13 seconds to do the cache lookups, but those cache lookups saved, I think, like 16 minutes. And then in another more extreme case, again, run for about a minute, there are about 2 million node functions, there are about 1 million hits, 1 million misses, but the hits, so all the lookups cost about 20 seconds in that run of like aggregate CPU time. I think it was 8 cores, but the saving of like runtime was about 1 hour and 12 minutes. So the thing is, like, I think initially you kind of understandably are worried about the overhead, but the reality is that in most programs, locality is real, and actually being able to reuse things and having a very pervasive runtime which caches things makes a massive difference to efficiency. So I think we've got enough time.
Yeah.
We've got enough time. There are lots of other great things you can do once you have addressability. So we're just going to give you like a very quick demo of like of one of those things, which is that you can build like much more declarative UIs. So we now have like a code that we can address. And you can build like a DSL to address the UI. In this case, the window is the outer thing in a tree, and that contains some kind of container object, which itself contains some labels and some text, right? So that's great because now you have something that's addressable. But on the other side, now we know the code is addressable. So we have this code which we showed you, which somebody wrote. But what we can do is we can pick up that code and we call it binding. So we can bind these variables into the UI. So we have these magic arrow operators, which are part of a DSL. And the arrow operators show that when the text box changes, we want the UI to like force its values into the running code. And when the running code, when the value of the function, the bottom thing, when that changes, we want that value to be pushed back out into the UI. Now, when we run this thing, we run it in a completely different environment, but because the scheduler owns the execution, we're still running the same code that the user originally wrote, but now we can detect when you call fuel cost, like what do you depend on when you call fuel cost? And as that function runs, we can detect, oh, you do eventually depend on rate. So now when the rate changes, we know that we have to reevaluate the fuel cost. So we can actually show that. So here, like Gjeta's changing the number, you need to press tab for the number to update.
What? I'm updating.
Oh, okay,
Yeah.
cool. Sorry, you are. It's hard to see, the light's very bright.
Yeah,
Here, when we change these values, the UI is pushing the new values into the calculation engine, but the calculation engine knows which values on the screen are affected by the changes that it's receiving, because when it ran the initial state, it could record what was touched. So now we can like create UIs. We also, we've got a kind of demo which we can't show the code for because the code's a bit longer, but just to show that we can build like much more complex UIs, we have this demo which is just to show that this isn't a toy. You can build like very extensive applications that we have like sitting on numerous desktops inside of Morgan Stanley that are used on a daily basis. And that's like it's a very powerful construct to be able to mix paradigms like UI and sequential processing together, but still use the same original business logic code. Got it?
Yeah.
Right. Okay, so this is the code that the user writes, and our big aim on this platform is to make it so that the code that people write is more like the code that they want to write. And hopefully we've shown that in this talk today. I did want to just talk a little bit about how we did it. We have an extremely supportive stakeholder group within the bank. They've backed us. It's been a very difficult project, but they're also very demanding. And I think that you kind of need people to be a bit demanding, because when you give them something that isn't quite right, they need to speak up and be vocal. And I think that tension's worked really well. We definitely didn't start with a plan. We tried things and they didn't work, and we've come to this conclusion, and we think it's a very valuable one because we're able to do we're able to parallelize these things. We're able to manage change. We're able to execute across many machines at extreme scale, and I think that's really good. We do have a booth here, and some of the people who worked on this project who have made massive contributions are here today. And thank you very much. There's actually so many of you, I can't list you all, but it's a massive team effort to build something of this size and complexity. But it's not all over. We've got loads of stuff we still need to do. We really need to improve the way that we manage all of our execution so we can drive even more efficiency for the applications that sit on our platform. There are things that we can do to kind of improve the readability of the code. Because at the moment there are decisions that we made earlier in the project about openness, and everything can tweak everything, and that's not necessarily great. And then there are other optimizations that people are working on around the project. Dimitri can talk to you about PGO. It's going to be awesome. And there are other things like Serge can talk to you about how we move processing onto other machines inside of the grid. There are things that we can improve there. And we are hiring. So if you're interested in this stuff, if you're interested in building applications on a platform like this, or you're interested in building this platform, we are hiring. I think it's a great project to work on, and come and see us. We have a stand, and there will be numerous people. We are going to do some questions now, but if we don't get time to get to your question, come to our stand or come and find us afterwards. I'm not sure how long we've got, but we'll take some questions now.
Thank you.
It seems like a reimplementation of Monique's tasks backed by a. This seems like a reimplementation of Monique's tasks backed with a scheduler with some lazy vals thrown in. It reminds me a lot of pure functional programming, maybe a little Scala Z IO with effects. How is it different?
Okay, so I think the big difference is that there is not the invasion of the type system of the runtime constructs. So in all those things you mentioned, like in my examples, they're mostly floats, right? Or doubles. So in my examples, the type that the program is dealing with is a double. It's not a future of cancelable of double. Mm-hmm. And so I think the biggest difference is that from a programming perspective, you're much closer to dealing with the actual problem you're trying to solve, which is that you're dealing with these doubles, and these runtime execution concerns are not dominating your code. But so, for example, like cache activity, mm-hmm. We had somebody, we decommissioned a system that mm-hmm. was with this, and somebody very diligently went through all of the code in the old system mm-hmm. and kind of classified what it was doing, and 20% of that code was actually doing cache management. Right. So now that code doesn't exist at all in that system. I mean, obviously it exists in the infrastructure, but in the same way that memory management code doesn't exist in a Java program, cache management code doesn't exist in that mm-hmm. code. So I think that's the key difference, is that we don't invade the type system with the concerns of execution, which I think is one of the reasons why it's hard for the very good ideas that exist inside of functional programming to make traction with the kind of general population of programmers in the world.
Mm-hmm. Okay, thank you.